Thank you for attending this session. If you came here, I guess you are interested on Lambda and streams as I am. I'm Joana. I work at Ocado Technology. Today I'll talk about Java 8 key features, Lambda expressions, and stream APIs, and some performance analysis I did on them. So briefly, I just want to talk about the company I work for. Ocado Technology is an English company with offices all over Europe. They provide software solution for online grocery, either being a shopping platform or the technologies involved in warehousing and delivery. So as I said, they have offices in Europe. Their headquarters is in Hatfield in England. I come from their office in Barcelona, so I did quite a long travel up here, not as long as some other presenters that came from Japan and so on. And they have 2 offices here in Poland. So on this presentation, I'm going to talk about lambdas and streams, but basically I divided the theme in 4 main topics. So each topic I'm going to talk about some theoretical assumptions, some background, but mostly the performance analysis I did for each of these topics. So what was my motivation to decide looking into Lambda expressions and streams? And as most of developers nowadays, I started getting really addicted to them. Like some years ago, about 4 years ago, when I started shifting my mind on how coding and started using them, I had to shift a lot to get used to them. Then I really use them all the time, and the team I code with, we use it a lot. So they've been very, very adopted recently. And mostly because of the benefits they bring. So the most clear benefit they bring is conciseness. So they're much less verbose. So with much less code, you can perform same functionalities at traditional previous style of coding. They're much more readable. So it's very clear the intent of the code when you use lambdas and streams. You have to read less code from your code base, and because you use declarative style, the intention of the code is very clear. They also enable to use a block of code around. You can pass this block of code as parameters, and you use them elsewhere in your code base. And I think the most important is that they are less error prone. Each operation in a stream, for instance, they are very enclosed in itself. It's very intentional what you're going to do. So you don't have to imperatively say all the logic and all the conditions you need in your functionality. So it's harder for a developer to insert error using streams and lambdas. But at the same time, I was already using that a lot, and then I realized I don't know how are they implemented and processed under the hood, either by the compiler or the virtual machine. And I had no idea how they performed, if they performed worse or best than a for loop or an anonymous class. And most of us, we use them and repeat how we saw them used around the code, but we don't know if there are different possibilities and approaches to make them perform better. So what I'm presenting here today, it's investigation of varied topics. I tried to limit myself not to go too deep in a topic, because you get like reading more, investigating more, and you start to get addicted. And I didn't want to get just one topic and go too deep on it, because I think there wouldn't be any benefit of going too deep into just one topic. I'm also not going to go really deep how they are compiled or how they are interpreted. I'm just briefly mentioning that the focus of this talk is not compiling or interpretation of them. And I benchmarked some assumptions I found on the internet about how they implement and how they should behave. I benchmarked if in reality they perform better or worse. Some of the performance results I show here, they are not available on the internet. So I tested some scenarios that I read the theory of how they should behave, but I did not find any actual performance results for those scenarios. Other scenarios, I found similar results, but then I tried to test with different variables and different conditions. So as I said, I'm presenting performance results. I did all the benchmarking using Java micro-benchmarking harness. I'm testing and presenting the results of the average time it takes in milliseconds for an operation to be performed. And I did 20 iterations of warm-up, so all the results here is guaranteed that it's hot code, so it's optimized by just-in-time compiler for all the results. And I tested on Java 8, which is what I usually use on my machine. But I want to mention I did exactly all the same tests that I'm presenting on Java 11, and I got very similar results and the same conclusion. So I didn't want to extend showing those both results. I'm showing the results only for Java 8. So the first topic is Lambda versus anonymous classes. So Lambda anonymous classes, you achieve the same functionality with both of them. It's just the syntax is very different. So here we are just doing some random functionality using an anonymous class, just getting the length out of a string. So actually very simple operation. And this is the equivalent if I use a Lambda. So it does exactly the same thing with one line of code. And the exactly same thing if I use method reference as the Lambda and as the exact same functionality as the anonymous class. So the amount of code and the readability is very clear. But how anonymous classes are processed? So anonymous classes are processed at compile time. Just as any class, at compile time, the compiler generates a new class file, something like this. At runtime, every time they are invoked, they are loaded and verified. The lambdas, they are implemented and processed very differently. So they are actually implemented at runtime by the virtual machine, not at compile time. And the invoke dynamic that was introduced in Java 7 for dynamic languages is what is responsible for instantiating a Lambda, calling a Lambda factory, and at runtime generating an instance of the Lambda as a functional interface type, so the function that the Lambda is implementing. And it converts the body of the Lambda into an instance of a method. And in a method reference, it doesn't need to do this extra processing for the body of the Lambda as a method. It just goes straight to the instantiation of the Lambda itself as a functional interface. So I analyzed the performance on hot code in the conditions I mentioned before for 500,000 strings. But just to remember, in this case, the difference should be on startup, which is something I didn't measure. Because on startup, if you imagine each Lambda, if you instead of using a Lambda, you use an anonymous class, at the startup time, it would be processed each anonymous class to a new instance of a class. So the impact will be a startup time. Once the code is running, the performance for each of those cases is about the same. So in this case, the performance doesn't vary. You've got a very different way of interpreting both different styles of code, but you got the same performance once the application is already running. So for Lambda and anonymous class, there was no significant performance difference at a running application. And to save extra processing, it's good practice to use method reference. So when your IDE tells you this Lambda can be a method reference, it's not only because it looks nicer, it's because there's no need to give extra work for the machine. Next topic is capturing versus non-capturing Lambda. No, I didn't test that case. I tested a thread case when I talk about parallel stream, which is a different case. But for that case, exactly, I did not test. Anonymous classes. And that in a hot patched code, yeah. Can you give me your contact afterwards? Because I would be very interested in that. That sounds very interesting. I was actually, when I performed my test, I was a little bit disappointed to get the same performance, because I was hoping to have either way different performance results. Special case, no? Yeah. Yeah. Yeah, but yeah, I would like to, if you can talk afterwards, I'd like to that. Thank you. Okay, so capturing and non-capturing lambdas. So what is a capturing lambda? So a capturing lambda references variables from its surrounding scope. So the variable it references is not on its body of code itself. So for instance, in this example, it's referencing BD, which is a local variable. And a non-capturing lambda does not reference variables from the surrounding scope. It only references variables within its own body of code. And that does, maybe talking like that might not seem important, but they end up being implemented differently and having an impact on performance. Capturing lambdas, they are evaluated every time they are invoked at runtime. And for each time, they would generate a new instance. A non-capturing lambda, they are evaluated and instantiated only once. And every time they are invoked, they return the same instance. So capturing lambda, because they have to be reevaluated each time and return a different instance, they are not optimized automatically, and non-capturing lambda are. To check if indeed there was a difference on the instantiation of non-capturing and capturing lambda, I did a profiling analysis using Visual VM on a sample project. I tested this code, which contains a capturing lambda, referring to item, which is outside itself variable. This method containing many method references that refer to variable also outside this body, so also a capturing method references. And a non-capturing lambda within this method that reference to a variable within itself. So as soon as I reach an endpoint that triggers the method, all the methods that invoke those methods containing those lambdas. So as soon as I activate those lambdas, what I saw in the profiler was, for the first lambda, I got 1049 live objects, so it's the amount of time that lambda was invoked. For the next method, I've got, for each method reference, one type of lambda, but 43 live objects is the number of times it was invoked. And for the non-capturing lambda, I only got one instance. So in practice, what is said in theory, I could easily observe with a profiling tool. Sometime after the invocation, they were very easily cleared by the garbage collector, so there's no problem of memory on this case. It's not that they are stayed. And I did the performance analysis on a running code using 500,000 big decimals. I tested a capturing lambda for referencing a final static variable. The type of variable the capturing lambda is referring to makes a difference in performance. A capturing lambda referring a local variable, and a capturing lambda referring to a class variable that was not final and not static, and a non-capturing lambda. So on a hot code, I got this result. Using capturing a static variable as reference, as base reference, if I'm using local, if I'm referring to a local variable, the decrease in performance is 20%. So remember, is milliseconds, average milliseconds per operation. So the higher the bar, the lower the performance. So it took longer when I reference a capturing variable for the performance for the operation to take place. And if I use a non-capturing lambda, then I increase performance in 40% for this scenario. So on this topic, capturing lambda do tend to have lower performance. The type of variable the capturing lambda is referring to also impacts the performance of the lambda. But with this, I'm not saying use or don't use capturing lambda, because sometimes you have to code your code this way or that way, and you need a variable or not. But have in mind, if you have this flexibility and milliseconds in performance are important for you, and you know this, when you code and you have options, then you know what option to choose. The next topic, the third topic, is stream versus loops. This is the topic when I went on the internet to read about it. That's the one that more people talking about. There are many benchmarks and many people talking how streams perform much worse. Difference between streams and loops is mostly on how you see the code. I mean, how easier it is to use a stream to loop through and iterate through a collection. So streams are much more concise, loops are much more verbose. With streams, I can use declarative style programming, so it's very clear what I'm doing. And with loops, I have imperative style. Streams, I can enable pipeline operations. So within the operations, I operate through a stream, which is an intermediary state of the collection. It's not the final state, before I output to the final state. So within operations is very lightweight processing. And loops is lightweight processing in general. It's something we'll be using for a long time. So the compiler and the virtual machine are very used to them. I did a performance analysis with 500 integers and primitive ints. For loops, of primitives, I used this code. So I had an array of numbers. I was just summing numbers up. And the equivalent would be a stream where I iterate through arrays. Observe that here I'm using a stream on this format, array streams. That is to guarantee I'm iterating through an int stream, which is a stream of primitives. I mentioned that because I saw in the internet people comparing something like this with a normal stream, not an int stream. So it would be iterating through integers, and then the performance is lower. So if you don't do a guarantee using int stream, you are kind of cheating towards making stream look worse, like perform worse. And then looping through a list of objects. So here I also saw some benchmarkings using this. So in this case, even though I have a list of integers, I'm auto unboxing them and then I'm processing through the primitive. So it also performs better. So you're also cheating to make loops perform better than streams. So I changed and I analyzed properly looping through integers to guarantee I'm not cheating towards here or there. And the equivalent of that would be a stream of integers doing the same thing, just summing up all the elements and getting the final result. So for 500 integers or ints, this is the difference of looping through primitives and using a stream with primitives. The decrease in performance was around 680% if I use int stream. And if I use looping through integer as objects and stream integers, the decrease in performance is around 145%. There are some considerations, though. We don't usually use a stream just to sum up elements. We use a stream for much heavier functions. So using streams to do such a simple loop maybe is not really fair on the performance of streams. So also, we can use operations to increase the performance, which would be map to int or reduce. So I did another performance analysis now with strings, and I tested a stream that does filter, filter the strings by the length size, maps the string to its length, so to primitives, and get the minimal value using a comparator. I did the same but using reduce instead of minimum comparator. And I did the same using map to int. So when you use map to int, you get int stream. So you transform your stream of objects into a stream of primitives, and you enhance the performance. This compared to a loop that is doing exactly the same. I have for to iterate through the collection of strings, and a conditional, and a comparison, and return the minimum value. So if here we can already see how it looks much better using stream than using for with conditionals and so on. What I got in this case was loop compared to stream, plain stream, decreased the performance in 570%, so it was much worse for this case to use a stream. But to observe, and what's more important, when I use a combination of reduce and map to int, the performance of stream is much better. Then I only have a 75% decrease in performance. So for this, to topic, for the scenario I tested, loops are faster than streams. If I'm iterating through primitives, the difference in performance, even if I guarantee I'm using a stream of primitives, the performance difference is even higher. The performance depends on the operation type. So if you're interested, I think it's really interesting to try the diverse operations you can use with a stream and check how you do using loops and conditionals, and it might diverge a lot, the results. Yes, it's the next topic. It's very interesting as well. So it's the last topic. Also, and I think the most important in this case, depending on how you use the stream approach, you increase the performance of the stream very much. So yeah, the next topic is, and the last topic, is parallel stream versus sequential stream. So there is a lot of excitement involving stream on how easy it is to implement parallel processing with a stream. You just use a keyword and you guarantee all the other operations you do in the stream will be performed in parallel. We have to keep in mind that parallel processing contain the overhead of processing the collection before and after the preparation. So you need to prepare the collection, you have to separate the items, and then you have to stitch together the result. Because of this before and after processing, parallel processing performs better for the product of the number of elements multiplied by the time it takes to process each element. So if you don't have many elements and the procedure you're doing in each element is very lightweight, they will probably not bring you any performance benefit. It can actually slow down, exactly. That's what we are going to see. So also, there are some operations in stream where parallel processing perform not as good as they should. So they would be sort, distinct, and group by. So for those, it's usually no benefit using parallel processing. But anyway, let's see what I tested for those cases. So I tested first 500,000 strings using a sequential stream, filtering the string by length, replacing a character in the string, and then returning a list. Exactly the same thing using parallel stream. So for 500,000 strings, for this operation, parallel stream performed 68% better. So I got an increase in performance of 68%. It was 68% faster. But then I thought, usually at least at my work, I hardly have to iterate through 500,000 elements. I mostly have to iterate at 1,000-something elements. So what would happen if I have 1,500 strings? In that case, it's worse to use parallel stream. So just by using parallel stream, I decrease my performance in 45%. And if I'm iterating through 100 strings, then the decrease in performance is even worse. So I totally destroy my performance if I'm iterating through less elements. As I said before, depending on the operation, parallel stream perform better or worse. So I tried with distinct before the other operations. So I got the streams. I've got the stream. The first thing I do is I guarantee I get distinct elements, and then I perform filter and pick and so on. The same thing with parallel stream. So I do distinct before. And then something that could help my performance in this case. So I know distinct will make parallel stream perform not as great. I used unsorted before. And I tested this for 500,000 strings again. So if you remember, the previous benefit was around 68%. Here is just 23. So just because I'm using the instinct, the benefit of using parallel stream decreased a lot. But if I used unordered before, then I got back to the 68% benefit. All this was on a single thread scenario. All this I tried, but what if I'm in a multi-threaded scenario? So parallel streams by default, if I can configure them to perform different, but by default they use the number of threads I have on my system -1. My machine has 4 cores, so I have 8 threads. So using parallel stream is guaranteeing to use 7 threads. So it's performing concurrently with 7 threads. So I did the same, knowing I have 7 threads on my parallel stream available to perform the operation. But I did a multi-threaded scenario. So I imagine there are 4 threads attacking my method at the same time. So invoking the stream at the same time. In that case, the benefit of parallel stream for 500,000 strings, if you remember in the beginning it was 68% for 1 thread scenario. Here it decreased for 21. If I have 7 threads, which is exactly the number of threads I have available on my parallel streams, then the performance is the same if I use sequential or parallel stream. If I have 8 threads, then I start to have a decrease in performance if I use parallel stream. 24, the decrease in performance is even higher, and so on and so forth. So from parallel stream, what I concluded from this test is that they optimize and enhance the performance in a very restricted scenario. This restricted scenario, you have to consider how many threads I have available in my system and how many threads are going to attack concurrently the stream. The number of elements in the collection that I'm iterating through, and the complexity of the operation, if they are more or less time-consuming. So to sum up, with this presentation, don't mean to say use a stream, don't use a stream, use Lambda, use anonymous class. Each application has its own profile. You have to consider if your application, you need the gain of milliseconds of time in an operation. In JBCN conference in the beginning of this year, there was a presentation by Julian Viet that for their application, they actually refactored all their lambdas to non-capturing lambdas because they needed these extra milliseconds. And they actually gained a lot of performance just by doing this refactor. You have to consider readability and error prone. So in the code snippets I showed here, it was very clear how readable and how easier to code them they are. You have to consider if the team of developers involved, they like to use Lambda or streams, if they are used to that. And when benchmarking, you have to consider all the scenarios available. As I said, especially on streams, you can easily cheat towards this and that way. So the way you use the loops, the way you approach the stream, you got a difference in performance. So if you're benchmarking, no benchmarking is a final rule. It's never 100% conclusive, but you can test different scenarios and see towards you get the most fair conditions you are comparing. I think the most important is that either for streams or for lambdas, you can make them perform better just by the way you approach the code, just by the tools you use. So keep using streams, but test different functionalities, study different functionalities and approach, and start using them as best practice in your code and try to replicate within your team. Because as your application scales, this little difference in performance by just the style you code might pile up. That's it. Thank you so much. If you have any comments, this is my Twitter, and I'm available for questions here or otherwise. Thank you.